Hi everyone, welcome back to Mathematics for Engineering 3. This is the second chapter of the course, okay, which is the higher order linear differential equations, okay. In the previous chapter, we learned how to solve the first order ordinary differential equations, right? We have several techniques. For example, the separable equations, the homogeneous equations with linear coefficients, exact equations, and those that need the integrating factors, right? And some first order linear equation, Bernoulli and Riccati, right? So we have several techniques to solve the first order equations. But in this chapter, we're gonna be looking at the higher orders, okay? The higher order equations. Well, so let's begin, okay? The higher order linear differential equations. First, it's going to be an introduction. We're going to talk about what general linear equation is. Okay, so here is the general linear equation. So if you look here, the general linear equation of order n is an equation in the form it is in this form. So basically, you have the derivative of y, right? The nth derivative of y by x, and the coefficients of the derivatives are the function of x. Okay, they are function of x. So there is no y. Okay, there's no y. Okay, it's only x here. Only x here in the coefficients. Okay, and if the coefficients of each term has no y, okay, there's only one term, only one y here, and the rest are just function of x. Okay, and on the right hand side there's no y as well. We call this equation a linear equation of nth order when n is the highest order of the derivatives. Okay, or we can write it in this form. Okay, when yn is actually the nth derivative of y. Okay, yn minus 1 is the n minus 1 derivative of y. Okay, so the point is that the coefficients must be functions of x. Okay, and the right hand side here, they need to be function of x, and if they are in this form, we call them general linear equations. Okay, and if Rx is 0, we call this equation, the general linear equation, homogeneous linear differential equation. Okay, so we call it homogeneous linear differential equation. Okay, it is related to the homogeneous in the when we did the first order equation, but I would love to to tell you that you should think of two chapters as the separate chapters. Okay, so forget about the first chapter. Okay, just focus on the second chapter first. Okay, don't forget them. Okay, because you need them in the exam, but I'm just saying that in order to solve the second orders, you can think of it as a totally separate chapter. Okay, so if Rx is 0, we call this equation homogeneous linear equation. Okay, and if Rx is not 0, we call it non-homogeneous linear differential equation. Okay, so just to sum it up, the linear equations are the equations in these forms. Okay, when the coefficients are only function of x, no y, and the Rx here is a function of x as well. Okay, and if Rx is 0, we call the equation homogeneous linear differential equation. And if Rx is not 0, we call the equation non-homogeneous. Okay, let's look at some examples. Okay, so the first one, this one is a, you look here, the coefficients, see, there are no y, see, so this one is a homogeneous linear equation of order 2. Okay, it's the homogeneous linear equation of order 2. Okay, how about the second one? You look here, the coefficients are constant, right? It's basically 5 minus 4 plus 1 minus 1, right? Those are the coefficients, and they are not, there's no y in it, right? So you can call it as a function of x because there's no y. Okay, so this is the, and you can see this is 0, the same as that. So it is a homogeneous linear equation of order 3. Okay, the next one, as you can see here is constant, which are function of x. In other words, there are no y's in there. Okay, and here this is Rx, which is not 0. So this one is a non-homogeneous linear equation of order 3. Okay, is non-homogeneous linear equation of order 3 because Rx is not 0. Okay, how about the other one? This one is, as you can see, is constant, function of x, constant, and here is Rx is not 0. So again, this is non-homogeneous linear equation of order 5. Okay, the order is the highest order of the derivative. Okay, so it's the non-homogeneous linear equation of order 5. Okay, so right now you know what linear equations are, right? And when it is when they are homogeneous and when they aren't homogeneous. Okay, in this chapter we are going to be looking only at the equations which are linear. Okay, and at the beginning of the chapter we're going to be looking at the homogeneous linear equations. Okay, and in the second half of the chapter we're going to be looking at the non-homogeneous. Okay, but they need to be linear. Okay, they need to be linear. Okay, for non-linear equations we're not going to be looking at it right now. Okay, not in this chapter. Okay, cool. So before we actually solve the linear equations, whether or not they are homogeneous or non-homogeneous before we actually solve it. First, we need to know one jargon or one technical term, which is linearly independent. I think you probably know it from, I don't know, I'm not sure if you did linear algebra, but if you did linear algebra, you would know the linearly independent. Okay, but anyway, let's assume that you haven't studied linearly independence before. So if the functions f1, f2, blah 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 until fk are linearly independent, if c1 f1 plus c2 f2 plus ck fk equals 0 for all x, if and only if c1 equals c2 equals ck equals 0. Okay, or in other words, we call that these f are linearly independent if and only if, okay, if whenever c1 f1 plus c2 f2 plus blah 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 ck fk is 0. You need to have that, or these constants are 0. Okay, and what if when f1 f2 until fk are linearly dependent? Okay, is the opposite of linearly independent. Okay, which means that you can find c1 c2 c3 blah 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 until ck which are not 0. Okay, which are not 0, and it makes this 0. Okay, those c make these 0. Okay, so you need to know what is linearly independent. Okay, linearly the functions are linearly independent if the constant times the function, the sum of the constant times the functions is 0, if and only if all the constants are 0. Okay, let's look at some example. f1 and f2 is sin x and cos x. The question is, are they linearly independent? Okay, so first I'll need to let c1 and c2 be any constant. Okay, and c1 cos x, okay, which is, let's say, c1 f1 x. I'll just write like this. We see that c1 f1 x plus c2 f2 x, which is c1 cos x plus c2 sin x, is 0 if and only if okay, at the end if we want to show that they are linearly independent, we need to show that c1 and c2 are 0. Okay, why? Because if you go back to look at the definition, if these are 0, all the c must be 0, so that you can say f are linearly independent. Okay, so c1 cos x plus c2 sin x is 0 if and only if, okay, if and only if is 0 for all x, right? For all x, as you can see, is 0 for all x. Okay, so if and only if, let's say, if I pick x, which is 0, if I pick x, which is 0, you need to have that c1 cos 0 plus C2 cos sine 0 equals 0, isn't it? But sine 0 is 0, cos 0 is 1. So you have that C1 is 0. Right? 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 And whenever you have C1 is 0, you have that C2 sine x must be 0 as well. C2 sine x must be 0 as well. Why? Because if C1 is 0, it means that this guy is 0, which means that this equals 0. Okay? Okay? For all x. Okay? But as you know, sine x is not always 0, right? Sine x, it is not always 0. Okay? It is 0 if x is 0, pi, 2 pi, and blah blah blah, right? But it's not always 0. But this guy is 0 for all x, which means that C2 is 0. Okay? In that case, we can say that C1 and C2 are 0, which means that F1 and F2 are linearly independent. Okay, guys, this is not the main focus of the second chapter, okay? But I am teaching you so that the chapter is complete, okay? I want to make the chapter complete, so you need to first know about linearly independent, okay? But it's not the main focus, okay? The main focus of this chapter is to solve the linear differential equations, okay? Cool. So next, I'll introduce you another term. She's called Schwann Skin. Okay, Schwann Skin. The Schwann Skin is of F1, F2 to Fk, denoted by W of F1, F2, F3, blah blah blah, Fkx, is defined by this. And this is a determinant, okay? It's a determinant here, right? From high school, you remember how to compute the determinant, right? The matrix, okay? So basically, if you have kf's, okay, for the first one, you get the first f, the second f, and then the kth f, and you keep, differentiate k minus 1 time, okay? It will be clearer when you see the example, okay? But let's say this is a Schwann Skin, okay? So the theorem says that if there exists a such that the Schwann Skin of a is not 0, you can say that F1, F2 until Fk are linearly independent on I. Okay, so if there exists a such that this is not 0, okay, so you can say that F1, F2 until Fk are linearly independent. Okay, I know, guys, these are abstract, okay? They are not for you guys. You are soon to be engineers, right? So you don't care much about the theorem, about the abstract ideas. But to make the chapter complete, so I need to teach you, okay? So just bear with me for the first chapter, okay? Because for the first section, okay? Because it's gonna be about the theorems and things. Okay, it's gonna be a little bit more abstract. Okay, it's a bit more math than engineering. Okay, so if there exists an A which makes the Wronskian equals 0, okay, if the Wronskian equals 0, we say that all the F's are linearly independent. But how about, guys, this is the method of language, okay? We say that if there exists an A which makes the Wronskian 0, F are linearly independent. But how about if we can't find any A such that the Wronskian is 0? Okay, does it imply anything? Does it mean that the F are not linearly independent? Can we say that? The answer is no. The answer is no. The answer is we can't really conclude anything. Okay, this is what, pure mathematicians, love to do. If they say that if there's an A which makes the Wronskian 0, we have that the F are linearly independent. But if there is no such A that can make the Wronskian not equal 0, we can't say anything. Okay, that's the point. Okay, so let's look at this example. Are F1, F2 and F3 linearly independent? Okay, if you want to do it the hard way, you just need to prove that C1 F1 plus C2 F2 plus C3 F3 is 0 if and only if C1, C2, C3 are 0. That's the hard way. That's to prove it by definition. Okay, but because we know Wronskian, right? We know what Wronskian. So if we know the Wronskian, we can first compute the Wronskian of F, which is of F1, F2 and F3 at any point x. So what is it? Do you remember the formula? It is to have F1, F2, F3, F1 prime, F2 prime, F3 prime, and F1 double prime, F2 double prime, F3 double prime, right? And you find the determinant of that. Okay, and this is the, what is it? F1 is e to the x, F2 is e to the minus x, and F3 is e to the 2x. Okay, F prime is e to the x, Here is minus e to the minus x and e to the minus x, right? You differentiate this, you get this. Okay, and the last one is 2e to the 2x and 4e to the 2x. Okay, this is nothing. I just follow the definition here. Okay, we have F1, F2, F3, and then you differentiate down, you differentiate down. Okay, guys, keep in mind that the number of row equal the numbers of column. Okay, it's a square matrix. So if you want to find the determinant, what you would do is that you would first copy and paste the first two columns. Okay, I hope that you guys remember how to find the determinant of a matrix. Okay, so basically you copy and paste these two columns. Okay, after that, if you multiply down, that is plus, and when you multiply up, you get minus sign. Okay, that's from high school. Okay, so the Wronskian, the Wronskian is, what is it? Here is e to the x minus e to the minus x, 4e to the 2x, so it's minus 4 e to the 2x, isn't it? Okay, the next one is this guy, isn't it? So is e to the minus x, e to the x disappeared, so we have 2e to the 2x plus 2e to the 2x. And the third one is this guy disappeared, so we have plus e to the 2x. Okay, and then we have minus, what is it? If it goes up, you get here these and these cancel out, so you have minus e to the 2x, right? But you have another minus here, so it turns to be plus e to the 2x. Okay, I stopped drinking the milk tea. Okay, you might you might have noticed that why I am shooting the video, I have been drinking lots of milk teas, right? But I realized that during COVID I gained around 8 kilograms. Okay, within a couple of months. I realized that because 2 days ago I went to the university for the first time after a long period of online activity. So when I went to the unit for the exam, okay, I need to go there to invigilate the exam. Invigilate means to supervise the exam, and I needed to take a grab bike to the university. I couldn't drive there because I was late. Okay, the reason I was late was that I couldn't find any trousers to wear. Because as you notice, when I'm home I always wear the t-shirt and the pants, the short pants, and I didn't notice until I needed to go to the university. I needed to wear the long trousers, right? And I was looking in my wardrobe. I couldn't find any trousers that I could wear. They are too tight. Okay, it's like the gap of my trouser is like this. Okay, so I decided I need to stop drinking the milk tea and keep exercising. Okay, otherwise I'll get even bigger. Anyway, so where were we? Here is these cancel out, right? So we have minus here, minus e to the 2x, and because if we multiply up we get another minus, so it's plus. Okay, the next one would be this, and these cancel out, right? So we have 2e to the 2x, but we have the minus sign, right? So it's minus e to the 2x. And the last one, these and these cancel out, so we have 4e to the 2x, but with the minus sign. Okay, so let me deal with this guy. This cancel out. So we have, what is it? This is a 4, 3, which is minus 1. So we have, what is it? Minus 5 e to the 2x. Okay, let me check that all the things are correct. Okay, so here is e to the x, e to the minus x, e to the 2x. Okay, and then we differentiate, we get this guy. Okay, which is correct, and then we find the determinant, right? So here we get minus e to the 2x. Here we get 2e to the 2x. Here we get e to the 2x. Okay, and we multiply up here, we get e to the 2x as well, and here we get minus, oh sorry, you probably have seen it already, we have 2 here because this is, these and these cancel out, so we have 2e to the 2x, so we have minus 2e to the 2x. Okay, so sorry, let me go back a little bit. So it's gonna be 2 here, so it means that this cancel out with this. Okay, so what we have is minus 6 e to the 2x. Okay, so the theorem says that if you can find a number a which makes the Wronskian not 0. Okay, if you can find the a which make the Wronskian not 0, the f are independent. Okay, so here if I pick a, I choose a equals 1. Okay, so I have that the Wronskian of f1, f2, f3 of a is minus 6 e to the 2a, right? The Wronskian of x is minus 6 e to the 2x, so the Wronskian of a is minus 6 e to the 2a, which means that this guy is minus 6 e to the 2, which is not 0. So we can conclude that these f1, f2 and f3 are linearly independent. Okay, they are linearly independent. Well, note if you have e to the m1x, e to the m2x, e to the m3x, blah blah blah, until e to the mkx, and m1, when m1, m2, let's say it like this, m1 is not m2, is not m3. Okay, let's say that they are all different. Okay, we know that these guys are linearly independent. Okay, so the exponential functions, if they aren't the same, they are linearly independent. Okay, that's the conclusion. Okay, so why do we need the linearly independent property? The reason is that because we have these three theorems. Okay, the first theorem says that assume that a0, a1 until an are continuous and an is not 0. Okay, and y1, y2 and yn. Okay, this is the important point. y1, y2 to yn are the solutions of the general homogeneous linear equation, right? These guys are linearly independent if and only if you can for any x, the Wronskian is not 0. Okay, guys, don't forget, before this we only have one way, which is this way. Okay, when you can find a value a which makes the Wronskian not equal 0, we have that f1 to fk are linearly independent, but here is both sides. Okay, so whenever the Wronskian is not 0, you have that the solutions are linearly independent, and when the solutions are linearly independent, the Wronskian must not be 0 for all x. Okay, and we have another theorem says that when y1 and yn are the solution and they are linearly independent, okay, any solution of y can be written as the linear combination of y1 to yn. Okay, so let's say, guys, let's say if y1, y2, y3 until yn, we have n solutions. Okay, and if they are linearly independent, we can say that the combination of those solutions is also a solution. Okay, and the last theorem is the most important theorem. Okay, it's the reason why I need to give you this introduction section. Okay, so the theorem says that the general solution of star, okay, the general solution of homogeneous linear equation is this guy. Okay, where c1, c2 until cn are constants and all the y's are linearly independent solutions of the star. Okay, so let me conclude. If you want to find the solution of this equation, which is the homogeneous linear equation, okay, if you want to find the solution of that, first you find n solutions. Okay, you get the solution 1, solution 2, solution t3, which is y1, y2, y3, blah 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 until yn. And then if those y are linearly independent, the combination of those y, okay, the linear combination of those y's is the solution. Okay, and that is the end of this section. Okay, guys, I know it's a little bit abstract. Okay, it's not very engineering, right? It's more mathematics. But to make, as I told you again, it's not the main focus for our chapter. Okay, you just need to know. Okay, but I don't think this will be in the exam. Okay, but if it's in the exam, I'll let you know. Okay, I'll let you know. But usually this is not in the exam. It's there just to make the materials complete. Okay, you need to know some theorems to know that, you know, if y1 and y2, y3 until yn are solutions and they are linearly independent, you can say that the combination of those is linearly, the combination of those is a solution. Okay, and how to check if they are linearly independent? You can use Schwann Skin. Okay, if Schwann Skin is not 0 for all x, you say that is linearly independent. Okay, but don't forget guys, exponential functions, they are always linearly independent. We're gonna use that in the next section. Okay, so in this section, let me sum it up. First, I introduce you the linear equations, right? The general linear equations, and one is homogeneous, the other is not homogeneous. Okay, the equations are linear when the coefficients are functions of x. Okay, there's no y in it. Okay, and if Rx, which is the right term of the equation, is 0, we call that homogeneous. If it's not 0, we call it non-homogeneous. Okay, and then we looked at the linear independent property, right? If the functions are linearly independent if c1 f1 plus c2 f2 plus blah 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 plus ck fk is 0, if and only if all the c's are 0, right? That is the definition. But we have Schwann Skin to check, right? The Schwann Skin say that if you can find a, that the Schwann Skin is not 0, you can say that all the f's are linearly independent. Okay, and then we started looking at the equation, the linear equation, right? When all the y1, y2 until yn are solutions, and if they are linearly independent, okay, you need two conditions: all the y are solutions and they are all linearly independent. The combination of those, which is c1 y1 plus c2 y2 plus c3 y3 plus blah 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 plus ck yk, that is the solution of the homogeneous linear equation. Okay, and that is the end of this section. Okay, see you guys in the next section. Okay, bye bye guys.